The idea of teleportation has captivated the human imagination for centuries. The ability to travel instantaneously, to bridge vast distances in the blink of an eye, has fueled countless science fiction stories and captured the dreams of many. But what was once relegated to the realm of fantasy is now edging closer to reality, thanks to the mind-boggling world of quantum mechanics. We're on the cusp of a new era of transportation, one that could redefine our understanding of space, time, and the very fabric of reality. Quantum teleportation, as it is known, promises not the teleportation of matter itself, but something even more profound, the teleportation of information. Imagine being able to transfer the complete quantum state of an object, its every characteristic, its entire essence, to another location, effectively recreating that object without ever physically moving it. This is the tantalizing possibility offered by quantum teleportation. It is a concept that stretches the limits of our intuition, challenging our fundamental understanding of the universe. Yet as we delve deeper into the subatomic world, we are discovering that the rules governing this realm are far stranger and more wondrous than we could have ever imagined. To comprehend the true nature of quantum teleportation, we must first abandon our classical notions of how the universe operates. In the quantum realm, the familiar laws of physics give way to a world governed by uncertainty and probability. Here, particles exist in a superposition of states, occupying multiple positions and possessing multiple properties simultaneously, until the act of observation forces them to collapse into a definite state. It is within this ethereal realm that quantum teleportation takes place, not as a means of transporting matter through space, but as a way of transferring quantum information, the very essence of a particle's being. This information encodes the particle's properties, its energy, its momentum, its spin, everything that makes it unique. By transferring this information, we can effectively recreate a particle in a distant location, as if it had been teleported instantaneously. But how is this even possible? The answer lies in one of the most bizarre and counterintuitive phenomena in the quantum world: entanglement. In the quantum realm, objects are not defined by their physical attributes in the same way they are in our macroscopic world. Instead, a quantum object, like an electron or a photon, is defined by its quantum state. Think of this state as a blueprint, a set of instructions that dictates the particle's properties and behavior. Imagine a spinning coin. Before it settles, it exists in a superposition, both heads and tails simultaneously. Its quantum state encapsulates this uncertainty. Once observed, the coin collapses into a definite state, heads or tails. Similarly, an electron's quantum state encompasses its energy, momentum, spin, and other properties. This state is not merely a description of the particle, it is the particle. Two electrons with identical quantum states are indistinguishable, essentially twins. This concept is crucial to understanding how teleportation works. We are not moving the physical particle, but replicating its exact state elsewhere. One of the most perplexing aspects of quantum mechanics is the role of the observer. Unlike in classical physics, where observation is seen as a passive act, in the quantum world, observation fundamentally alters the system being observed. This is the crux of the measurement problem. Imagine trying to pinpoint the exact position and momentum of an electron. The very act of measuring one property inevitably affects the other. Heisenberg's uncertainty principle tells us we can never know both with perfect accuracy. This intrinsic uncertainty poses a significant challenge for teleportation. If we were to directly measure a particle's quantum state in order to teleport it, we would inevitably alter it, destroying the original and creating an imperfect copy. This is where the ingenuity of the teleportation protocol comes into play. It circumvents the measurement problem altogether by leveraging the power of entanglement.